Hello and welcome to one of our solved problems for the Homework 16. In this case, a string with a linear mass density of mu equals 0.0093 kilograms per meter is fixed at both ends. A 5.0 kilogram mass is hung from the string as shown. If a pulse is sent along section A, which is where tension A is in our diagram, what's the speed in section A and the wave speed in section B? So it is kind of difficult in order to understand where all these quantities are going to come in initially. But what I would say is to do is to first write down all of the quantity values that you know for wave speed in a linear string. In that case, this is V is equal to the square root of tension over mu, where tension is the tension in the string and mu is the linear mass density, the mass per unit length. If this With this, we know mu already. We are given mu, but we don't know the tensions in the two strings. And we should know from previous chapters that the tensions in the two strings are going to be different because they're at different angles with respect to the horizontal, which means that the velocity going through each is going to be different. So what we have to do is find the tensions in these two strings. And the way that we find this is generally going to be if we have a bunch of forces and we don't know what the one of the forces is, but we know what the acceleration is. In this case, the acceleration is zero because acceleration of this point is going to be something that we can call zero, even though it does technically go up and down a little bit along with the waves. But for the most part, we can just say that in the same way that we say that tension and the length of the string isn't affected that much by the oscillation of the string, we can say that in this approximation, the acceleration at about that point, about that knot at the center of the diagram, is going to be equal to zero. So with this known, if we know the acceleration, we know that ma equals F net, or ma is equal to zero because acceleration is equal to zero. Therefore, F net y, or the sum of all of the forces in the y direction, is going to be equal to zero, and the sum of forces in all of the forces in the x direction is going to be equal to zero. It is just a statics problem, which you have done several times before at this point in the class. Even if I don't think we've done any explicitly on the lectures, we have done these several times in the homeworks. So what is Fy? So you can obviously see that TA has Fy equals zero because it's completely along the axis. And the weight pulling down, mg, the weight pulling down from the 5 kilogram mass is completely in the y-axis. But what is the component of TB that is in the y-axis? In this case, TBY is equal to the hypotenuse times the sine of the angle because it's the opposite of the angle and the overall tension B is the hypotenuse of this force. Therefore, the component of tension B along the y direction is TB sine theta, and the component of tension B along the x direction is going to be equal to TB cosine theta because its sine is opposite over adjacent, or opposite over hypotenuse, and cosine is adjacent over hypotenuse. Therefore, by multiplying by the hypotenuse on both by multiplying the hypotenuse by sine of theta and cosine of theta, you're able to get the opposite side, which is TBY, and the adjacent side, which is TBX. So FBX or FY is equal to TB sine theta minus MG, and FX is going to be TB cosine theta minus TA, and both of those are equal to 0. We only have one unknown on the y side, so we're going to solve for that first. TB sine theta is equal to mg. Therefore, TB is equal to mg over sine theta. And then plugging it in over here, we have mg over sine theta, which is TB, times cosine theta minus TA equals 0. So TA is going to be equal to mg times cotangent of theta. Just subtracting out negative TA on both sides, so adding TA on both sides. So you add TA on both sides, and you simplify the cosine theta over sine theta to be cotangent of theta. So this is pretty uh, clean. That's pretty easy. Uh, what we get for our final question, which was initially what is the wave velocity of both of these waves, is that tension A is mg cotangent of theta. So VA is the square root of mg cotangent of theta over mu, and VB is the square root of mg over mu sine theta. Thank you very much. I'll let you go.